Okay, so then the 3 p.m. So we start the 57th the ASE seminar. So I'm Takashi Mukami from the University of Tokyo, and thank you very much for coming to this seminar. And today this seminar will focus on the visualization and the HPC infrastructure and the visualize the large data. And in this, the ASE seminar is held irregularly, and when we have visitors from the overseas. Today we have the 3 invited speakers. So first, Dr. Tim Gerrit from the RWTH Aachen University, Germany, and also the second invited speaker, Marcel Kruger from the same university, Aachen University, Germany, and the third invited speaker is Dr. Takuma Kawamura here. So he came from the Japan Atomic Energy Agency. So okay, so now we start to the first talk. Okay, so please go ahead. And the first speaker is Tim Gerrit. So please join me in welcoming Tim Gerrit. So thank you very much. And the title is the scientific visualization for and with the HPC infrastructure. So okay, so you have the 40 minutes, including the Q&A session. So please start your talk.
Yeah, thank you very much. It's very nice to be here. I hope you can hear me. If there's something wrong, just drop a message. I know that some of you have already heard about our work, so there's going to be some repetition in here for the people who we've already met, but for everyone who's new, nice to meet you virtually or in person. And yeah, my name is Tim, and I'm here together with Marcel, and we are originally from Aachen University, as already introduced. And just a second, yeah. And we are here because we're part of a project, a nationwide project in Germany called Nationales Hochleistungsrechnen. That's the German word for it. And it basically translates into National High Performance Computing Center in a way. But so it's very similar to a project that is here in Japan too, which is JHPCN. And that's also why we're here, because both projects decided to work together, and that's why we had the honor to be here for the last almost 3 months to work at University of Tokyo. And the general idea was that Germany decided to get more resources into a nationwide infrastructure to make it easier for every researcher in Germany to get access to high performance computing, right? To get free access to large compute nodes and fast compute nodes, but also get access to support. So people who already know what they're doing, how to work with this kind of hardware, how to make your code faster, and also expertise in different domains that need high performance computing infrastructure. So that's the whole idea. It should be easier for every researcher in the country to get access to that. So that's the general gist of it. And in the whole of Germany, there were 9 so-called centers or universities that were selected because they do have high performance computing computers already at site, typically tier 2 clusters that would then be made available for all researchers. We specifically work in I would call it subgroup. It's called NHR Forces, and the Forces stands for Computational Engineering Sciences. So this is a group that focuses on everything that has to do with computational engineering sciences, which means people who do fluid simulations, who work with medical data, who work with energy conversion and things like that, right? And our project is designed in a way that we have basically 4 pillars, and you can think of them as the domain directions. So those are people who develop novel models to describe fluid dynamics, novel models to have faster simulations of blood flow, right? Things that are very domain focused. And we have this orthogonal group of people that help those groups to improve their code to make it better suited for high performance computing. So we have groups that only focus on how can you make your code run faster on massively parallel infrastructures. And we have a different group that helps you come up with better ways to structure your data and save it and share it with others. And one of these parallel groups is the visualization group. This is the group that I've been leading for the last couple of years and that we're both working in. So our major goal is obviously to bring visualization to national high performance infrastructure. And while this sounds very nice, the question is, why is visualization that important that it would need their own group? And how does it even look like to bring visualization to such a project? And for the first question, I always like to bring this very simple example. This is data that was actually calculated on one of our high performance clusters. This is how data typically looks like if you work with it, right? It's a file with some numbers in it. And if you would like to now make sense of it, you could try to look at the numbers and try to guess what they're doing. But if you take those numbers and map them onto something geometric, like a position in space, you can immediately see that this is actually a simulation of neural structures in the human brain. So each location is actually a neuron, and we can collect the calcium levels. We can see how energy is converted and sent from one neuron to the other. And humans are very good to use their visual senses to see those patterns and see those structures and immediately see, for example, something goes wrong or something is more active than something else. And that's the big benefit of visualization. And we specifically work with scientific visualization, which means we don't deal with any kind of data, but we focus on data that has a physical relevance, right? We deal with data that describes physical phenomena such as weather, pressure, temperatures, mechanical stresses, things like that, things that are typically that can typically be described as spatial or as quantities at spatial locations. So that's what we're typically dealing with. All right. So a different aspect, besides just providing something people can see, is we also try to provide applications that allow users to explore their own data and make sense of it by using and connecting visual representations of their data, right? Visual analysis software that allows you to dig into things that you find interesting and then focus on the details that you are interested in. This is one of the big and major parts of our work as visualization scientists. All right. Obviously, the moment you do this for high performance computing users or researchers, you end up with a whole lot of problems, especially because the data is becoming unbelievably big and very hard to handle. Oftentimes, it's just not feasible to get the data off the big clusters onto a local system to then visualize it. Standard programs most often don't really work with this amount of data, but it's also a different side to it. If simulations get more detailed and better and more accurate, it also means that their complexity is rising and it becomes more complicated to understand what's going on. Maybe we have multiple variables that are connected with one another, and making sense of that, seeing those connections is also something that becomes inherently more difficult. And the final part is obviously that workflows become more difficult, right? Many people develop their codes on their laptop first, and then they run it on a large cluster. But it would be good to use the same visualization approach, but make it adaptable to those different workflow requirements. So these are the challenges that immediately arise. And our goal in this project as visualization scientists was to enable users, and this can be any kind of user within a high performance computing background, so researchers, developers, or just operators of programs, to make use of advanced visual tools to improve their workflows, right? So make it easy for them to get access to visualization, any kind they would need. And this goal is quite nice, but it obviously, the devil is always in the details, right? There's always going to be challenges. And over the last couple of years, we realized that there's 3 main challenges that we needed to tackle and are still tackling. In the next couple of minutes, I want to share with you some of those, what those challenges are, and some of the examples of how we tried to address them. So the first one is a technical challenge, which is the obvious one, right? Data is really big. What happens if data is distributed on multiple nodes? How do we handle the technical requirements of handling data, sending data from A to B, being able to render things that are distributed? So all the technical challenges that are involved in coming up with visualization. The second part are methodological challenges, which basically means maybe the way how we used to look at our data doesn't work anymore because it's too big, it's too large, it's too complicated, and we might have to come up with new metaphors to understand data, especially if we deal with, for example, large ensembles of simulations. So, of course, if it's only like 4 or 5 members, we can maybe put them side to side and look at them. But if it's hundreds of them, we need to find novel ways to describe the overall information that is encoded in those collections of data. And the final thing is a community challenge, which means we can only solve problems that we know of, and people can only use solutions if they know of solutions. So it's very important that the high-performance computing users and the visualization community grow closer together to share and address the issues that are at hand. Give me a moment. I try to maybe make the video smoother. Let's see. I don't know if this is working now, or if it crashes everything. A little bit, maybe. Okay. All right. So let's first talk about the technical challenges, because we realized there's actually 2 ways to approach them. One is to say we need to make visualization ready for high-performance computing. And what I mean by that is that typically a lot of visualization tools that people know and people use, they are not ready to be used on high-performance computing related data because it's too big, or it doesn't run on a cluster, or things like that. So one of our major things is to provide users with tools that already exist that can handle these kind of problems. So this is an example we did for some collaborators back in Germany. So they have a large-scale simulation of a flame front, and there's some soot forming in the center, and they wanted to have a look at the amount of soot over time, and if they change something to visualize in the model, if there's going to be more or less soot. But they were not able to look at this kind of data because it's massively big. I don't know, Marcel has some details on that later on, how many terabytes the whole simulation is. And we helped them to bring ParaView, which is a very famous open source tool that many people know, onto the cluster and give them the means to render this kind of video to look at their data themselves. Because there are tools out there, but many don't really know how to use them or where to get them. So this is one big aspect. A second idea is that sometimes the data we're dealing with is so specialized that we need to come up with novel tools on our own. So for example, we have a collaborator in Jülich that creates these very, very detailed 3D polarized light imaging data. And you can imagine this data is created, you take a human brain of a dead person, obviously, and you freeze it, and then you slice it into unbelievably thin slices, and then you shine light on it, but it's polarized. And then you slightly change the polarization, and this will result in a different reflection of the light. And you collect all this information. What you get is a very fine-grained information of how fiber directions are distributed inside the brain. But this data is so big, and it has to be on a cluster that there's no standard tools to look at this data. So we had to come up with a way to get data from the cluster onto the machines of our collaborators, like local laptops or whatever, while still using the performance that is still on a high-performance cluster. Finally, we realized that the problems that we're having for our one-off solutions, they reappear every now and then, which means that it makes sense to provide tools that makes it easier for other visualization researchers to address the same issues. So we worked on libraries or on wrappers and things like that, that other people can use to, for example, allow users to have something that is portable. So it runs quickly on your laptop, but if your simulation knows that we're actually working on something that has access to GPU memory, or we work on a large cluster, it will try to improve the performance by automatically detecting that and scaling the visualization code. So it would always be most performant based on the problem that based on the hardware that you're using right now. So for example, we worked on a geodesic ray tracer that would allow you to look at black holes. And this is now a library that can be included into different research code to most efficiently render, for example, black hole geometry, space-time around certain space locations. So this was one part, right? Trying to look at what does visualization already do and how can we change it to make it accessible to high-performance computing users. And a different idea is to think about how does data or visualization need to change itself. This is like thinking about, can we maybe use compression to send data more quickly to a visualization algorithm? How can we maybe compress the data in a way that the visualization will be good because it will focus on a specific kind of the data while we can compress the rest much more. So trying to come up with ways that keeps visual fidelity high while reducing file sizes, things like that, right? Or can we make use of limiting the impact of, if we distribute data on different nodes, can we collect information without needing the access to different nodes? So we can compute things like tensor information on the fly, right? Thinking about how can we collect and deal with data differently because we're working on a high performance computing cluster. The second approach is to think about how can we make simulations ready for visualization. And this is basically what we've been doing here in Tokyo, because a lot of people who write simulations, they do it with their simulation and their models in mind. They don't, when they start working on this code, they probably don't think, I need to take care that in the end, I can come up with a very efficient visualization process. So especially we have been working with collaborators in Germany that have code that is like 20 or 30 years old, that's still written in Fortran, and they don't want to change their whole code base just to have a nice image in the end. So one of our biggest issues we have is how can we help those researchers bring visualization into their code without them having to change a lot. So this is just a small example, and Marcel will also show this in detail what's happening. In the end, what we want to have is we want users to get access to a running simulation that is on a cluster. And this is an example of what we did. So it is a fluid simulation of flow around a plane. And we have an interactive application that allows you to change what you want to visualize. As you can see, it updates because it will resend the updated visualization data once the next cycle on the cluster is done. But the important part is that the visualization and the simulation are decoupled in a way. So the simulation has been instrumentalized once, and they can run it whenever they want without having to think about what the visualization is doing. It's a decoupled thing. And as I said, Marcel will focus on this part in more detail. And the second, then changing from technical challenges to methodological challenges, is a different approach where we, as I said, try to come up with novel ways for people to understand data that is complex or large or multi-dimensional or multimodal, right? And typically, a lot of high-performance computing users, they don't really have time to look into what are the most promising visualization tools out there. So a lot of our work is bringing this information to the users because they have to think about how to improve their models. So we'll try to tell them, these kind of, for example, quantities are best understood using these and those tools. We do this through like support and collaboration. And a different idea is to come up with novel visualization methods and tools and methodologies, and also interactions that allows people to look at their data from a new perspective. So this is a short example using tensor data. So for example, this shows stresses inside a material. There's like a powder, and the more powder there is, there's going to be more energy pressing on this little area at the bottom. So those are 4 different results of different levels of energy. And there are features that might be interesting, so-called mode surfaces. They can describe how mechanical stresses are distributed throughout the field. And if you do this for all the members and you can collect them, you see that there's some areas where most of them have these features, but in other areas they are less prominent. And we can come up with new descriptions of this kind of data that summarizes the behavior within the whole field, right? And this is what you can see on the left side, where color, for example, indicates a measurement of uncertainty. So how certain can I be that there is going to be this kind of feature throughout all the ensemble members? And we can put this to the extreme. So for example, on the left side, those are degenerate tensor locations. So locations where a stress tensor, for example, has repeated eigenvalues, and this can have a specific meaning in your domain. And those are, this is showing extracted features of only 10 members from 1,000. And you can see there's a lot going on. It's very hard to understand what's actually happening. And by trying to summarize it and coming up with new features that are based on distributions of values rather than extracting values from each and every member, we can summarize it and give people an easier way to understand. Like on the right side, you can see we have this clear line in the center that is the most likely location of a degenerate tensor to appear. And we have this yellow surrounding area that gives like a confidence interval of how likely it is of these features to appear throughout a whole ensemble of tensor data. And of course, while doing this, we try to make it in a way that it's very efficient, that it can be calculated very quickly, and it can be calculated on massively big data, so we can give out these novel tools for people to understand their data. When I talk about novel exploration, I don't only mean novel ways of looking at the data, but also novel ways of interacting with the data. And we have a lot of collaborators that approached us saying they want to look at their data in virtual reality, for example, or augmented reality. And luckily, we have at our lab, we work very closely together with the virtual reality team in Aachen. And we do have one of the largest cave installations. That's, if you don't know what a cave is, it basically is a room inside a room where there's images projected onto the walls. And if you are inside the room, you're wearing shutter glasses that are tracked. And if you move around and you change your view, the images that are projected will also change. So it's basically like wearing a head-mounted display, but you don't have to wear it because the whole room becomes the display. So you have a sort of true three-dimensional view of the data you want to look at. And many of our collaborators wanted to look at their data inside a virtual reality application. And of course, this has a lot of problems because massive data and high frame rates that you need for an application like that, there's always a problem to get the same thing running at the same time. And this is also something that Marcel is going to be talking about in a moment. But what we often try to do now, of course, is we look into what are the most convenient ways to work on something like this. So can we maybe make use of game engines to make this more accessible? Because game engines have a lot of advantages. Or can we make also looking at those simulations more accessible? So on the right side, there's an augmented reality simulation of a sound simulation inside a room that was shared with collaborators. So those are all different aspects we look into, all with the aim to provide users novel insights into their data. All right. Finally, I'm quickly going to talk about community challenges, because as I said, this all just works because we know about the problems that arise in the high-performance computing community. And for this to work, there needs to be exchange. And very often what we saw is that when we start talking to people, we hear similar problems popping up all over again. So it seems like that information is not really well traveling from one community into another. So what we try to do is do something like this, right? Have talks to share the insights that we have and share the experiences that we have with these communities. We do invited talks, and we also try to grow a network of people that work at the interface, like people that want to use visualization and people who want to bring visualization to high-performance computers. So what we also do is we do workshops and summer schools, things like that. But what I think is the most interesting thing is we try to provide gateway tools. And what I mean by that is we want to make it easier for both users, high-performance computer users and visualization people, to get a glimpse of the other community. So for example, visualization researchers have a hard time getting access to large and complicated data. So what we try to do is we make this data accessible from some of our HPC users, or we try to, as NHR does, give free access to high-performance computing nodes so they can try out things. So it becomes easier that a visualization researcher will try out a thing on massively and complicated data. And also the other way around is we want to make it easier for high-performance computing users to try out visualization. And that brings me to one example. It's a database of visualization examples called Dave that we've been developing for the sole reason to make it easier for people to use visualization. So this is a small demonstration. This is a website that is live. You can find it on dave-vis.com. So it's accessible. And if you're a user or a domain developer or something like that, you can just go on their website, type in the kind of data that you're dealing with, like what is the dimensionality? Is it dealing with, I don't know, like fluid problems, or is it medical data? And the system will try to give you hints and tags on what describes your data best. And if you've settled to something, the system will give you a collection of visualizations and visualization tools that are out there that could be applied to your data directly. So you can look for it, you can browse it, change the filters a little bit. And if you found something that looks interesting to you, you can just select it and you get like an article that tells you all about it. How does it work? Maybe the papers that you can reference, look at it, you can play around with a live visualization on the website. So you don't have to install anything besides a browser, and you need internet access, of course, but you can immediately look into different visualizations that are out there that might be suitable to your problem. And the best part, I think, or the most relevant part is up to this point, this is more or less helping you to research an appropriate visualization tool. But the relevant part is that you can now create a customized container that runs this specific visualization. So you can go ahead and press the customize button, and then it will ask you, do you want to use your own data, or do you want to use the example data that is here is used in the example? And you can basically give it just a path to your data. You can say, is it supposed to run on Docker or Singularity? Is it going to be put out via a Slurm job, or does it run locally, or does it use MPI? So it will take all this work that you typically have to do to customize it to be running on your system, and put this into a single script, which you can then run on your machine, which will then do exactly that. It will run the visualization code on whatever data you give it, and it will do everything for you by following a simple script. And it not only means that you already can have a final visualization of the data that you're dealing with, but it also gives you a starting point if you want to learn how visualization was used to create the image, or like the visualization that you're doing. So because we make sure it uses like simple Python language, you can look at the Python file, change parameters, run it again. So you don't have the burden of trying to learn a lot which libraries are used and what is out there. So we push you into a direction that helps you get started much more quicker. Okay. And this is maybe another example of what we try to do. This is a project called Deep Switch, where we looked into how people typically try to access large-scale data that is actively updated all of the time. And it's very complicated for new users to understand how do you actually get access to this kind of data? How do you convert it? How do you do things like that? And once again, we settled on easy interfaces that, for example, lets you decide to select a region on your own, and then a script in the background will go into different resources. So this is data from NASA, and we'll grab the data from their servers, process it in a way that will make it accessible and smaller, and calculate some data on it, so that in the end, it will be loaded into a web tool. Let's see if it starts, yeah, into a web tool, and it's already accessible. And we think about how to make it such that the conversion from simple tools to more complex tools becomes easier as well. So this is a view that you are probably familiar with, like 2D views. But by just clicking into the view, you can make it a 3D view, so you get an idea of that this data is actually not just the surface of the world, but it has depth information, and you can go ahead and try to extract interesting information such as vorticity, isocontours, which give you an idea of where circular ocean currents are moving along. And we can switch between time and spatial view to basically get a tracking of how those circular motions are moving over time, things like that. So the idea is make those things that can be used to get complicated and complex insight into data much more accessible by getting the infrastructure problems out of the way first. So I hope that through my presentation, you can see that through visualization, what we want people to be able to do is explore and evaluate their data or their simulations more effectively and efficiently, right? Especially about getting early insights into running simulations is very relevant, because often you have to wait until the whole thing is done, and then in the end, you have to guess if something broke along the way or it didn't. But it's also about providing more efficient workflows to work with this kind of data. And finally, of course, this is also a key to communicating the work that you are doing as high-performance computing users to the outside world, right? If you remember the video that we did, so this is something that is not only used to evaluate if the simulation is doing well, but you typically also use this to share it with stakeholders or with public, like you put it on your website, and also, or you put it alongside a paper submission, which of course also makes your work more accessible through visualization. All right, and this brings me to the end of my presentation. And the thing is that you can ask questions right away, but I know that Marcel is going to be talking about some of the aspects that I've been introducing. So it's very likely that some of the questions that you might have now will be answered later by Marcel. So my guess is we should switch to Marcel directly and then have a shared Q&A session for the both of us, if that's okay with everyone, right? Okay, thank you so much.
Okay, thank you. So, thank you. Introduction. So, okay, the second speaker is Marcel Kruger from the Aachen University, and the title is the Immersive Visualization Workflows for Large Data. So please start your talk.
Okay, thank you very much for the introduction. So I will basically pick up some points that Tim already mentioned. My talk will a little bit more about the technical challenges, but here we go. Okay, so yeah, we will focus a little bit more on the technical challenges, and the idea is that whenever we have a scientific visualization workflow, we have first to think about what do we really want to do. So we usually have a data producer that could be simulated data, but it could also be observed data, so it doesn't really matter. And we take the raw data and apply some kind of pre-processing, right? So for example, we want to derive the Q criterion or some vorticity. And after that, we want to extract some data from it in form of visualization primitives. So for example, if we have vorticity, we can use streamlines. If we have the Q criterion, we can use isosurfaces to take a look at specific Q values. And in the end, we want to have some mapping to a geometry that can be rendered by our usual rendering engines. So in most cases, it will probably be triangles. And the challenge is that we want to have user input in all of these different phases. And this will be a focus on the talk, that we want to take a look at how can we have user input at all these different steps, and how can we influence all the visualization workflows at the different parts. So the research goal in general is to improve flexibility. So we want to have a very flexible pipeline, but also reduce complexity, because as we heard, it's very challenging to get people to use these workflows if it's too cumbersome to use. So in general, in visualization, and especially when we consider HPC visualizations, there are two ways to go. So first, we have post hoc data visualization, and the second one is in situ data visualization. So what is post hoc visualization? It basically means we have our simulation, and in every time step, we save the field data, the simulation data, and we do it until the simulation has finished. So we are just dumping all the data onto a disk. And after simulating, we can then load it, pre-process it, and visualize it, right? And this is one example that Tim already showed. So it's the flame front that we saw. And this is a data set that was originally 120 terabytes. It was subsampled to 12 terabytes, so the visualization is done on the 12 terabyte subsample. But it's still challenging and big enough to do it on your laptop, for example. So in this case, we used the cluster to extract all the time steps in a parallel fashion. So we load each time step, we distribute the rendering, and then we collect all the individual frames and put them into a movie again. The big disadvantage, however, is that the simulation has to be finished first. So if we don't know, if we are still in an experimental phase where the simulation is not stable yet, it might be that after a few time steps, the simulation broke down or something. And the challenge is that we do not only want to have them as pretty videos in our presentations, but we also have the cave system that Tim already mentioned. So it's actually quite large. So it's 5 by 5 by 3 meters. It's 4K per wall, and we have 4 projectors per wall. And in the floor, we have 6K resolution with 8 projectors. And the tricky part is that we want to have enough visualization capabilities or performance. So we have a stereoscopic rendering, so it will be in 3 dimensions. And we have optoelectronic tracking to make sure that the user sees the correct viewpoint. And for that, we use a cluster configuration where each projector is equipped with its own cluster node. And we do synchronization via 49 GPUs to render out the final image to the user. So then scientists can visit us and, for example, take a look at different simulation results. In this case, this is also a combustion simulation where we can see the flame front. We can also see the OH concentration in the air. And the scientists can see the data in 3D. They can interact with the data in 3D, and they can also discuss it by being co-located and seeing the same things in the cave system. So why don't we always do post-hoc data visualization? Because the advantages are that it's easy to implement. So usually a lot of simulations are already doing some kind of writing files to the disk. For example, for checkpoint restarting and so on. And usually you also have access to all fields. which is a big advantage because then you can do exploratory analysis as well. So if you're not sure what you are looking for, you can use it to go through the data. And the saved data can be used otherwise, for example, for checkpoint restarting. So if you know that the whole field is loaded at time step 10 or dumped at time step 10, and you want to pick up the simulation at the same time step, you can restart again from the data. The disadvantages are definitely file sizes. So we usually also see simulations that have time steps that are way more than 1 terabyte. So you have a lot of problems or strain on your storage infrastructure, on your visualization infrastructure. And traditionally, I/O bottlenecking was also a big factor. So writing all the data to disk was traditionally very, very slow, and it's getting better with NVMe and so on. But it's still observable. And one of the more modern things that scientists are interested in is early feedback. So in the postdoc approach, you have no feedback until the simulation has finished. And this is especially for very large simulations. The combustion visualization, for example, is usually running for 2 weeks on a big cluster. So they want to have feedback early to see how the results are. So an alternative is in-situ visualization. And the idea is in situ visualization that we have an interwoven processing pipeline. So we simulate, we pre-process, and we already visualize, and then we can save the visualization or show the data live. And this has a few advantages, especially if you consider how we can do it. So there are 2 different flavors. Or 3, but 2 main ones. So there's tight and loose in-situ visualization. In tight in-situ visualization, the idea is that on the same node, we are doing the simulation, pre-processing, and visualization, which basically means we can use the memory from the simulation and point our visualization algorithms to the same memory region. We don't have to replicate data. We don't have to save data. And therefore, we have a 0 copy process, which is very efficient. The second way to do it is loose in situ, where we say, okay, we have a simulation on 1 node, and we send the field data that we're interested in to a second node and do there the pre-processing and the visualization on the second node. The advantage is that while the simulation is still ongoing, we can do the processing in parallel. So the idea is that tight in situ is basically a time sharing between the simulation and visualization. So while we are simulating, we are not visualizing. While visualizing, we are not simulating, because we cannot change the data in the memory because it's 0 copy, it's just pointed to. And in loose in situ, we have the opposite. Basically, that we say, okay, we do it in parallel, but we have the challenge of moving the data. So a rule of thumb to which method to choose is that if the time to copy the data is way less than the time to visualize the data, loose in situ usually makes more sense. And I think this is like the most efficient way and most flexible way. But also the more involved way is to do a hybrid visualization pipeline, where we do pre-processing or first pre-processing step in a tight configuration, so on the node, and then send it to the secondary nodes. And as you can see, there are a lot of different points where you can decide what to do at which point. So in summary, it is about complexity and also your use case. The memory access, the runtime impact, and the scalability and complexity really changes. So tight in situ is very efficient, and the runtime impact is basically visualization dominated, and you only need a few additional simulation codes, a few additional codes in your simulation code, sorry. And for loose in situ, the runtime impact is mainly transfer dominated. And the visualization can be scaled independently. This is very nice. but it also needs a lot of more orchestration, networking, and the same simulation calls. And hybrid, you can balance it nicely, but it's also way more complex to configure because you have to find the sweet spot about both sides. So the advantages are obviously that we have early feedback from the simulation. So after the first time step basically has successfully solved, we can already have a simulation and a visualization of the simulation. So we can see what's happening. We have less I/O plus storage. So if we are only interested in the derived data, we just have to save these things. And it's still compatible with the post hoc workflow. So what we usually can do is use the same APIs to also write the data to disk, and gives the same ability. So it's basically you set it up once, but you get a lot of flexibility for different use cases. So we don't lose it. It's just a little bit more complicated. So while in general, it's pretty compatible to most things, the real issue is with exploratory workflows. So if we have real in situ compatible visualizations, so meaning the visualization is derived in situ, then we are usually losing data because we are just writing out the visualization or the derived data, which can be hard with exploratory data analysis. So usually what you would do is do the slower offline approach to get an idea what I'm interested in. And then if I know, okay, this is a certain region that is interesting because it's very turbulent, or there can be some pressure issues, instabilities, then I can observe this region and do it in situ very, very fast. So if you want to use it, there in general a lot of different libraries available. Just to name a few popular ones are Sensei, Ascend, and Catalyst. And one of the problems is that the simulation code needs library-specific calls. So depending on the library you use, the number of calls varies, also the data container. So a lot of older libraries used ETK, which is very close to how data for visualization is used. The downside is that if I want to bring these capabilities to your simulation code, you still have to, or you also have an additional dependency, namely VTK, and you have to know how to use it. A more modern approach is Conduit, which is also HPC focused, and the syntax and the idea is a little bit more, I would say, JSON-like. So it's very easy to use, and you do not have to have a lot of visualization knowledge to properly integrate it into your simulation. One of the major problems is that most libraries couple their analysis and visualization capabilities with the code instrumentation. So for example, if you are using Ascend, then you only have access to the visualization and analysis filters and tools that are present in Ascend. So it's a very reduced flexibility. So how can we simplify this and make the problems a little bit less severe? So one of the problems is that often the visualization and the simulation are basically bringing together two different communities. They're computer scientists, and in there, they're visualization scientists, and a very small subset of visualization scientists are doing in situ visualization. And you have domain scientists, for example, physicists or neuro researchers. So if they want to use in situ in their whole simulation workflow, what often happens is that we would like to have projects that are horizontally sliced. So the idea is that a team working on a specific problem is composed of computer scientists, of domain scientists, and then each and everyone can bring their expertise and find one common solution. In reality, however, a lot of research projects are more like vertically sliced. So people in a lab are all visualization scientists, people in a lab are all domain scientists, and so on. So the problem really is, and this was what Tim talking about, is the gateway tool providing. So how can we get people to get into it? And the problem really came up in the Human Brain Project. And we had neuroscientists that wanted to develop tools based on simulation data. And they usually use Python. So they have a lot of different neuro science libraries to calculate derived data from spike trains, for example. And they love to use these Python libraries and the web technology. So it was hard to convince them to get away from that and into a C++ library, for example, which is commonly used for most in-situ libraries. So the idea was to make it accessible outside of any complicated libraries and really give an easy gateway tool to bring people into it. And the solution was the insight-in-transit pipeline. And the idea was to get rid of all the complicated protocols and dependencies and just use HTTP REST APIs, WebSockets, and JSON and protobuf. And provide users with the ability to do in-situ visualization by just using an HTTP library and a JSON parser. Also, the whole HPC complexity, like multi-simulator environments, MPI, data exchange, scheduling, etc., is completely hidden. So we have 3 different simulators that are working together. They're exchanging data. Basically, they are simulating from a brain region to a single neuron in different regions. And we just give them one access node to get data from that. And they don't know that it's a cluster, that it's running an MPI. They have just the single access node. So if we take a look at the example, okay, the video somehow is lost. So what you would have seen is that after the simulation starts, in the browser, you can open the visualization and it gets streamed into the browser just by using the HTTP protocol. So basically, we got neuroscientists to develop their tools and get data from the running simulation without using any specialized libraries or complex dependencies. And the key takeaway for us was that people really had limited experience with in-situ and transit, but they liked the idea. It's easy to see that it's a good idea to have access to data that is coming out of your simulation. But accessibility was a make or break argument. So people were not going to adopt it because it was too complicated in their mind. And the people also love to keep their existing software stack. I mean, if you have a neuroscientist community and all of them are using Python, they don't want to switch over as a community just to get a few more additional features. But once hooked, they are willing to invest a little more. So we figured out that once they saw that they get early feedback and they get like the very interactive steering of simulations, they really liked it. And they also began to adopt more complex ways because they thought about saving time and resources. However, you can imagine that if I have a single HTTP endpoint, this will not scale nicely. In neuroscience, it's kind of okay because you're doing a lot of simulation and you're interested in mostly smaller regions that are affected in the end. But there are also a lot of other things like CFD simulations where you're interested in the whole domain, right? And what can we do when scalability is an issue or it has to be good enough? So if we want to use more sophisticated libraries, we still want to have the same accessibility and flexibility. So one popular in-situ library is Catalyst 2, which is a little bit more abstracted than the others, which allowed us to create a middleware that is Catalyst 2 compatible, which allows to do a very modular design of in-situ workflows by combining other Catalyst 2 implementations into workflows. So why do we want to do it? I mean, if you have modular software, the structure is more independent, self-contained, and you have a high reusability, maintainability is easier, and in a monolithic, everything changes. So for example, if I want to change the isosurface extraction algorithm, I don't want to rebuild my whole visualization library. I would like to just rebuild my isosurface extraction algorithm. So we came up with this node-based configuration program where you can basically use different Catalyst 2 implementations. In this case, it's the ParaView Catalyst 2 implementation to build more complex workflows and combine them with other Catalyst 2 implementations and also logic. So for example, we are calling here the ParaView 2 library, and we are saying, okay, if we have a time step, then in every 10th time step, we want to branch, or we want to branch on the time step. And in every 10th time step, we want to print out the variables that are generated by ParaView. There are a few more building blocks, but they allow us to do quite complicated workflows. So one of these Catalyst 2 models, for example, is a module that can send data and images to your messaging app like Slack or MetaMost. And we can build this workflow where we take a standard ParaView instance. We are doing in-situ visualization of a pressure field, for example. And then with the branching logic, we can say on every 10th time step, we want to send a picture of the current simulation to your instant messaging program, or if the maximum pressure is over 200. So if we know that it's, if something is wrong, if the pressure is too high, we can also be notified. Okay, so once we get the data, we still somehow have to render and interact with the data, right? And what we like to do now, and we took a closer look at, is to use game engines also as a tool in visualization research. The advantage is that game engines, they have a lot of tooling. So you can build scenes like digital twins, for example. You can have animation tools, you have sound, you have rigging tools, and so on. Also, there are lots of resources and people are familiar with it. So if you're using new talent or new co-workers that are supposed to hit the ground running, so get productive really quickly, the probability that they use the game engine is higher than they used your custom rendering engine, for example. And we successfully use it for different projects. So this is a simulation and a visualization of an aerosol distribution in a classroom. And by using Unreal Engine, in our case, for example, we had access to the photorealistic path tracer, but the same data and same application can also be used to run in our CAPE system. And we do not have to change a single line of code because Unreal Engine abstracts all of that. And we can just reuse it. We also use it in the context of neuroscience, where we investigated how easy it is for novel users to build these applications themselves. Then the Flamefront example from before. However, the problem is that most game engines are missing critical pieces to use them for visualization research or visualization not only visualization research. So, for example, data analysis algorithm, scientific data visualization algorithms, and also in situ in transit capabilities and interaction for scientific data. So this led us to the development of In Situ, which enables a hybrid in situ visualization through Unreal Engine and Catalyst. So In Situ is a Catalyst 2 compatible implementation, and it provides bidirectional hybrid in situ pipeline for Unreal Engine. And the idea is to make use of this hybrid idea. And I said, like, game engines do not have visualization algorithms, right? So that's why we are using Catalyst on the same node to extract visualization primitives. So, for example, we are attracting a control line or streamline by using ParaView, but we do not use ParaView for rendering. We take these visualization primitives and turn them into rendering primitives, so triangles, inside of the game engine, where Unreal Engine is really good at. And if you're wondering why it's TCP and EUDP, it's because we want to support a lot of different platforms. So, for example, our cave, but also standalone head-mounted displays, and you don't want to have very specific data transport libraries that you have to compile on Android, for example, or on some other more limited resource hardware. So this is one of the results. And the nice thing is that all the terrain and so on, we used Unreal Engine, and it was really easy to do. And then the data, the real scientific data, is extracted by ParaView. In this case, it's the Q criterion. And then we do the visualization again in the game engine as well. So this is the video that we already saw, but just to give you an idea, each time step is actually a few gigabytes. So it's not terribly huge, but still huge. And we are only extracting the streamlines on the node itself. That's why it's a little bit lagging behind, because the position of the seeding plane is streamed to our HPC infrastructure. The streamlines are extracted on the HPC infrastructure, and we are just sending about 5 megabytes of data back to the visualization. And this visualization was running on my desktop PC in my office. And there was a just normal EduRoam connection, so it's not really a high-speed connection. And this is why hybrid is very, is giving you a lot of flexibility, because you can, of course, also think about extracting just a region and doing streamline extraction on local, and then you have a little more flexibility. But it really depends on the use case. So lastly, there are also, when we are talking about immersive visualization, issues where you really want to have an easily accessible visualization to users. So that's why we also, more or less as a side project, looked a little bit at interaction in VR. So the standard way to in VR to select things is raycasting. However, because of the lever effect, so if you're selecting an object that is really far away, you have a lot of shaking in your hand, and it's hard to select small objects. And Intent Select was a previous publication by other researchers, where the idea was that you spatially and temporally accumulate a score, which basically means the longer you are close to an object, the higher the probability is that it will select that object. And we extended it to introduce complex shapes, improve scoring, and additional parameterization to have a whole pipeline where the user can, for example, easily change from the rendering, the seeding, and influence the derived data, but also can influence the simulation in the end. So to conclude, visualization is a proven tool for data comprehension. But it should always ease scientific workflows. So if you're introducing visualization to your workflow and makes things more complicated, then you're probably not going to use it often. The idea we currently follow is to make single tasks easier to accomplish, so to improve like building blocks and allow them to introduce more flexibility in your workflow, and then combine these into larger workflows that do some complex task. So what we try to think or do is think about end users and not developers, because a lot of existing libraries and approaches are really focused at how developers interact with it, and not like end users, for example, domain scientists. And we also try to think about the scientific workflow holistically. So we are more considering from data producer to user that uses it, and try to improve the whole pipeline. Okay, so I think we still have some time to do shared Q&A.
Yes. So thank you very much. Okay, so now let's move to the last talk of this session. The speaker is Dr. Takuma Kawamura from Japan Atomic Energy Agency, Japan. So the title is In-Situ Steering of the CFD Simulation with the XR Technologies. Okay, so please start your talk.
Thank you. I introduce about the in-situ steering of CFD simulation with XR technologies. Our focus is a practical method to visualize, analyze, and control large-scale simulation while they run. Volume visualization displays physical quantities by mapping color and opacity. It reveals internal features. 3D structures are observed by manipulating the viewpoint. Interactive processing requires fast rendering speed, the order of second. I provide an interactive visualization application based on particle-based volume rendering, PBVR, enabling interactive analysis of large volumetric data. And PBVR is used across multiple divisions at JAEA. In-situ control technology allows interactive controls of simulation parameters while visualizing and observing the running simulation. With in-situ control, large-scale simulation can be exploited for design variable optimization. And VR visualization is effective for understanding complex three-dimensional dataset. And visualization of 3D point cloud data is key technology for digital twin that incorporates the physical world into the information space. As research challenges, visualization data size become bottleneck, requiring hours to days for in-situ steering of large-scale simulations. And conventional methods lack sufficient speed, making VR visualization of unsteady large-scale data difficulty. And integration of 3D point cloud data with conventional visualization methods remains challenging. Here is today's roadmap. We begin with PBVR core technologies, then our in-situ framework, followed by in-situ steering, remote VR visualization, industrial application, and 3D point cloud visualization. I'll talk about core technologies based on PBVR. Particle-based volume rendering, called PBVR, is important elementary method for our framework. PBBR converts volume data into particle data, and the particle data are projected onto the screen to generate volume rendering images. The particle data consists of position, colors, normals, and normals. The particles are randomly located in each cells by using Monte Carlo method. The screen has color and depth buffer, and each pixels are divided into subpixels. The projected particles are synthesized to calculate final pixel colors. The size of particle data is given by the pixel size. For 1,000 square images, cast quality requires 2.7 megabyte particles. That is several orders of smaller than the original data. On the other hand, finest image requires about 10 million particles or 27 megabyte data particles. So the particle data size is proportional to number of pixels and image qualities. In conventional visualization, simulation data are converted into the polygonal elements, and polygons are generated across the entire domain. On the supercomputer, these polygons must order to the viewing direction. And after the ordering, the polygons are sent to the user PC to produce images. And any changes of viewpoint forces the whole process to run again. For large datasets, the polygon is hard to transfer, and the ordering step causes heavy traffic. As a result, the visualization slows down on the supercomputer, and interactive view changes become difficult. As an alternative, PBBR compresses the particle data into megabyte scale. Particle generation runs on the supercomputer, image generation runs on the user PC, and together they form remote visualization models. With parallelized PBBR, we constructed the In-Situ visualization framework, In-Situ PBBR. The server-side processing cost stays under 1 second. Visualization data remain within a few hundred megabytes, and data transfer cost is kept low. Interactive image visualization is achieved by tightly coupling particle generation to the simulation. And by using file-based communication, by using the file-based communication on the login nodes, the file-based application writes visualization parameter to the storage, and the particle generation program periodically checks the storage. It's enabling communication with the user PC and supercomputers. To address multivariate visualization, a bespoke technique was developed, encoded expert image model for the multivariate data. And to obtaining the visualization that faithfully reflects the expert insight. We applied In-Situ PBBR into thermal convection flow simulation using AMR mesh consisting of 10 million cast level 1 mesh and 20 million fine level 2 mesh. Temperature is visualized, and the resulting image is compared to visualization software ParaView. Lower left image shows the visualization result by PBBR and ParaView. Total performance is also compared to In-Situ PBBR and ParaView. PBBR generates particle data at about 17.8 seconds and transfer it at 60 seconds in the very narrow bandwidth, 3 megabyte per second, very narrow bandwidth internet. And instead, and the rendering speed is 91 frames per second. Instead, ParaView Catalyst generates volume rendering image with 388 seconds per steps. And Inch PBBR showed 5 times faster performance to ParaView and achieved interactive frame rate. Our framework provides a multivariate visualization function. This example uses a result of convection flow simulation using 4 variables. The variable Q4 means temperature, and it is defined to the transfer function 1, T1. Single variate volume rendering shows temperature distribution. The lower disk means heat source. The variable Q1, Q2, and Q3 means flow vector, and its absolute value is defined by using algebraic formula. Our framework passes the user-defined algebraic formula and synthesizes new volume data at the simulation runtime. And our framework can also allow the usage of differential operators of variables. In this example, user inputs second invariant of velocity gradient tensor as new variables into a transfer function 3. The vortex structure is visualized as a white line. And we can merge temperature volume and vortex core volume by inputting the sum of the transfer function 1 and transfer function 3. So we can confirm the relationship between the temperature and the vortex structure. Next, we move from the framework to the In-Situ steering. In In-Situ steering, visualization proceed while computational parameters are modified during execution. Enabling this capability requires an additional input interface on the simulation side for parameter update. In conventional workflow, observation points were defined before the run of simulation, which made it difficult to optimize those points during execution. The In-Situ steering application enables parameter input and observation point definition while the computing is running. As a case study, contamination dispersion analysis in Oklahoma City in United States is considered, with 9 observation points labeled A through I placed along the urban streets. And these are monitored of the contaminant concentration. The figure at lower right shows the In-Situ steering GUI, where contaminant dispersion is examined in this 3D viewer, and concentration at the observation points are examined in the time series view. In-Situ PBBR's file-based communication was extended to implement in-situ steering. Visualization parameters specified by the user are sent to the supercomputer together with the computational parameters. And the inch sampler simultaneously sends particle data and observation data to the user PC. On JAES supercomputer HPE SGI 8600, the in-situ steering framework is applied to an Oklahoma City contamination dispersion simulation. Observed concentrations are assigned at the sensor points, and demonstration is performed to search source locations that reproduce the observations. In this video, in-situ steering is conducted while a batch job is running on the supercomputer. The spatial view shows the contaminant dispersion, and the time series view shows the evolution at the observation points. Observed values appears as blue lines in the time series viewer. By editing the visualization parameters, vortex structure in flow are revealed based on the display results. The user enters and updates the source coordinates that define the computational coordination. The coordinates are transmitted to the supercomputer, and the contaminants are released from the new locations. This control loop is repeated to understand the relation between wind condition and contaminant dispersion. From the new source coordinates, contaminant transport along From the new source coordinates, contaminant transports along street looks visible, and the time series view confirms that the observed concentration at the sensors are reproduced. With the conventional control visualization in a separate application, changing parameters and rerunning for feedback can take hours to days. With in-situ steering using in-situ PBBR, feedback is achieved in real time. We now move to remote VR visualization. We extended PBVR from 2D display to 3D VR. From head-mount display field of view, we compute left and right eye fluster and project particles accordingly. We implement this via OpenXR, so we can support many head-mount displays. With head tracking, we update the view continuously for smooth experience. We get and we target over 60 frames per second. PBVR helps because viewpoint change don't require particle regeneration. On JAES supercomputer, a debris cooling flow simulation was executed and VR in-situ visualization experiments were conducted. A device selection capability was added to In-Situ PBVR to choose between a conventional display and a head-mount display. In the experiments, PBVR sustained more than 90 frames per second and successfully achieved real-time VR In-Situ visualization of simulation spaces on supercomputer. Next, we move to industrial application. Support functions were developed to facilitate In-Situ control for OpenFOAM, a standard solver in the HPC field. A command line user interface is provided for changing computational parameters. OpenFOAM offers code simulation features that communicate with the external code during the execution via file-based data transfer. And the same communication files are reused as the input channel of parameter change interface. To easily couple OpenFOAM with VR In-Situ PBVR, a Form to PBVR adapter was implemented. This adapter converts OpenFOAM format coordinates, connectivity, and variable data into data structure usable by PBVR. The mesh structures supported includes structured grid, unstructured grid, and latest polyhedral meshes. Polyhedral meshes is used in modern finite volume method. For polyhedral meshes, additional vertices are inserted in each faces and at the cell centroid to subdivide the cell into tetrahedra. And our system is verified to this environment. The VR In-Situ PBVR is supported head-mount display, Meta Quest 2 and 3, HTC Vive Pro and Focus 3, and this is a capability of OpenXR library. And we confirm our application on supercomputer, JAE's supercomputer, and the University Tokyo of Miyabi and Wisteria and Riken Fugaku. Next, we move to 3D point cloud visualization. We process 3D point cloud within PBVR framework. It enables to integrate them with volume visualization. It is hard to conventional visualization tools. We process 3D point cloud within the PBVR framework to integrate them with the volume visualization. For example, we handled at Atami City in Shizuoka Prefecture, aerial surveyed point cloud of about 14.6 million points and combine it with an simulated field. This is test hydrogen benchmark test data. For geological disposal, the goal is to isolate radioactive waste deep within the stable bedrock for the long term. The rock damage is computed around the underground tunnels and integrates 3D tunnel point cloud with a damage field. we visualize the damage on the logarithmic scale within the clarified wide dynamic range in the single view. In this video, volume visualization is combined with three-dimensional point clouds and displayed in VR using head-mount display. The white line represents the analysis mesh used to compute damage, and this region and this region indicates the resulting damage field. The gray region corresponds to the rock, and the white region corresponds to concrete. By overlaying realistic point cloud data with volume visualization, the condition of the rock behind the tunnel wall, which cannot be seen directly, can be understood. PBVR enabled fast volume visualization using compressed particle data. We split particle generation and rendering between HPC and user PC, and we built In-Situ PBVR with file-based communication for interactive In-Situ use. On top of that, we implemented In-Situ steering of parameters and boundary conditions, demonstrated real-time feedback in contaminant dispersion, and extended PBVR to VR in head-mount displays. We integrated OpenFOAM for industrial studies and optimized vortex behavior in suction tank case. Finally, we unified point cloud and simulation data, including underground tunnel damage, in single visualization pipeline. Our software is open source and support major Japanese supercomputers, and provides convenient installers, and achieved about 3,000 downloads per year. Thank you very much.
Thank you very much. Okay, so talk finished. So thank you very much for coming, and actually I'm the work for the application, and usually I don't care about I love the visualization, but usually I don't focus on the simulation. But of course, the visualization technique is very important. So this is it was a bit good opportunity to understand that how to visualize or effective way to visualize that data. So, and thank you very much for the three speakers, and thank you very much for coming on all attending. Thank you. So we will take this session, and I think the next ASE seminar will scheduled on the October 1st, 58th, but that is not visual. December 1st. Sorry, December 1st. Okay. So, and that is not a visualization, so, but that is, so maybe if you are interested in, please join that seminar. So thank you very much, and now close this seminar.